So yeah, let us just continue. You can then just work meanwhile on test number 2, yeah? It handed in the last week, and we have now 3 weeks left, yeah? So today we are talking at first about the theory of mantle convections, and we have 2 theories of, I need just a better pen, theories of mantle convection. So there we are splitting now our planet like in a cake, yeah? So and then we have here one piece of cake, and here we have the second piece of cake. So and then is then just a cross section through the earth. So then we have here below, we have the core, yeah? Then we have here the lower mantle. Here we have then the upper mantle. So and here very above We have then our oceanic crust and the continental crust, yeah? So, and then we are making this again green. And then we have here a dipping slab. Dips here into the subduction channel. A better green. So we are making this so. So and now we have the convection cells, and there we have two models. The first model has the convection cells like this. So there you are bringing material down, and then here it becomes heated up and rises again up. So it is actually a convection, yeah? So and then we have, here we have then the 650 kilometer, this continuity. So and here we have also convection cells. The other one goes like this, and the other one goes like that, yeah? So that is the first model, and in the second model, so that is the upper mantle, yeah, that is here also the upper mantle. Here we have again the 650 kilometer continuity. Here you have the lower mantle that you have here, and here you have the lower mantle as well, and here we have the core. So, but in this second model, we have here also the dipping slab. Yep. So and then we have here a difference now. Otherwise I must not talk about two models. There we have also such cells, yeah. And I mean within the cell we have another cell, yeah, that is here the same. And here you have the next one. And so on. So, but here you do not have a convection, yeah? In the first model we have here in the lower mantle convection, in the second model not. So, and then in the upper mantle, we have we have 87 to 86 strontium ratio. Of about 0.7025. So, and if you are checking in our former class when we talked about the original strontium 87 strontium to 86 strontium, then you saw that the original from the chondritic is lower, yeah. So that means we have here an enriched value, yeah, that is enriched in the upper mantle. Because here we are changing always the chemistry, yeah. So because we are subducting oceanic crust, yeah, and therefore we are changing always the chemistry. And as I told you already a lot of times, I mean, the oldest oceanic crust is 200 million years old, whereas the oldest continental crust goes back 4,300 million years, yeah? And that is because the oceanic crust becomes frequently recycled, and since this planet exists, it has been recycled at least 20 times, yeah? So I mean, if you are looking here for the Fiji plate, it is very young, yeah? The oldest oceanic crustal rocks here, they are 47 million years, and I mean the youngest one that is just today. Yeah? I mean Tonga, you have this, okay, that Tonga does not belong to the Fiji microplate, but it's just close by. There the new island just popped out of the water 3 years ago, and if you remember from our field trip, we saw all these hot springs, and that is an indicator there is still magmatic activity. Yeah? So in the youngest volcanic eruption in Fiji, yeah, that was then 2,000 years ago, yeah, and that was in Kandavu. Yeah? So that means you have, and here in the lower mantle that has the lower mantle has no, this one is depleted. And this one is enriched. Because 87 strontium to 86 strontium was, the original one was more enriched. Because you have the decay to rubidium then. So, and that is relative enriched, and that is very close to the chondrite. So, and you know by now the chondrite is the original, or as the original composition at this time when the planet was formed, yeah? So, and that shows us that we have not a mixing up between the lower mantle and the upper mantle, yeah? So, did you get this? Here in the upper mantle, we have always the change in chemical composition due to plate tectonic processes, yeah? Every day magma, new magma becomes formed, so and therefore the clock starts always anew. So and therefore we have different 87 strontium ratios to 86 strontium ratios, and here in the lower mantle it is still the same since at least 4,200 or 4,300 million years. But sometimes, if I can have the board. But sometimes, or we are thinking from time to time, there is a mixing between the lower mantle and the upper mantle. What's funny? Or at least we are thinking there is a mixture. Yeah, that's nice, huh? So there's only sometimes there's a mixture or an interaction between the upper mantle and the lower mantle. Sometimes. Sometimes interaction between the lower and upper mantle. So, and that is therefore we have to study the different rocks, yeah? Therefore, we are making here at the top, again, an oceanic crust. So, and here we have again the spreading center, that is the Middle Ocean Ridge. So here we have water, yeah. Here we have again a sailing boat. So here we have the Middle Ocean Ridge in the middle, and you know the Middle Ocean Ridge, that is a P-morph, yeah. That is a P-morph, or at least with a good marker, it would be a P-morph. Something like this, yeah. I'm not trembling, I'm just drawing that it looks more natural, yeah? So, and then you have here the production of new melt, and that we are calling the P or N morph. So that means P or N morph, that is the same, yeah? The other say primitive morph, and the other say normal morph, yeah? So again, I told you very at the beginning in class that we have also the E-type morph, yeah? So and there again, I'm drawing here now the boundary. At 650 kilometer, yeah? So again, we have from time to time, we have an influx from that is the lower mantle again. That is the lower mantle here, sorry for that, because otherwise we have just to switch the board. So then we have here the upper mantle. Here we have then the upper mantle, here we have our 600 discontinuity in 650 kilometers. Here we have then the interaction with the lower mantle. And then you are creating here a volcano, yeah? And that is then the oil, yeah? You know that is the ocean island basalt, yeah? So in this ocean island basalt, they are called E-type of morph, or E-type basalts, enriched. That is enriched. So that means there are certain elements which are enriched, yeah? So and that is then the oil, the ocean island basalt, and they are completely different to the P or N type of morph, yeah? So and this is then the plum component. component. That is the plum component, and there we have this component inside which makes them enriched. So, and now we are continuing to discuss here the ocean island basalts, yeah? So, and there I need again the board, yeah? Sorry for disturbing. So in there we need now a picture of the oceanic islands. Oceanic islands. And these are then the oceanic island basalt, yeah? And I just told you they have a plum component inside. And that means they are enriched, yeah? Now we need again the oceanic crust. There we have now an oceanic crust. It's a little bit a weak oceanic crust. We are now making a stronger oceanic crust. So, again we have our volcano here. Then the water here on top. So now we are just going down to the, here you have the thermal boundary, you know it's very close to the surface. You saw it also always in the field, because that it is very hot beneath, yeah, 1200 degrees Celsius. That is very hot, and then everything becomes heated up at the surface. So, and then we are making here again our boundary layer in a depth of about 650 to 700 kilometers. So, and then we are making here now that we are cleaning now here. So, and then we are making here this plum component, yeah? So in there I told you just before that there must be an influx from the lower mantle or something else why they are enriched, yeah? Because just in the model before of the convection model, I showed you there is no interaction, yeah? So and now just a few minutes later I'm coming up with the next point, there is an interaction. So and then everybody is thinking, what the hell is this guy telling now, yeah? So here we're making again the OC for oceanic crust. And now we need the strontium isotopic values from the asthenosphere and those from the lower mantle. So then we have here the asthenosphere. Then we have here the asthenosphere, and then we have here strontium values in the asthenosphere. Ranging between, that is the 87, yeah, to 86 strontium, and that ranges here from 0.7022 till 0.7028. So and here we have in the plum component, we have higher strontium values. I told you they are enriched. 0.7028 till up to 0.7070. So and now we have to think about why I'm saying on the other hand, there is no influx from the lower mantle into the upper mantle, but now we have the change here in strontium values. So, and now, I mean, now the question is where these plums are coming from. Coming they really from the lower mantle, or is there another influx? And actually you should know it by now what's going on there. This one should be here. So what's going on there? Just remember last week our things in the feed tree. Everybody was there, everybody should know it, if everybody has always listened to me. So because here in all the Fiji Islands, these are oils. They are not depleted. There's a little bit of mantle component inside here because they have high nickel and chromium values, yeah. So, but actually they are compared to malt, they are depleted, enriched. So, and now what I told you in the feed. I told you that something else can hang around in this boundary between the boundary from the lower mantle and the upper mantle. So, and what did I tell you? What is hanging around there? Who the devil? I mean, what is responsible here in Fiji for these deep settled earthquakes in a depth ranging between 400 and 600 or 650 kilometers? I did not tell you that it is the influx from the lower valley. I told you something else. What is hanging around there? Slabs, yeah. So, and therefore, that is the plumb component. The plumb component. And the question is, where are coming plums from? So, and that is recent models. So that was the model before that plums sucking material from the lower mantle, yeah? In a depth down to down to 650 kilometers. The second model is how deep does subduction go? How deep does the subduction go? And there we have the third or next component. That is the next component. That is then recycled old recycling of old crustal material. So that means here we have the recycling of old material, and then we can just, I will just modify this picture, yeah? So then you have just to make this picture again in the modified version, because you cannot wipe it out, yeah? I mean, you could, yeah? But it is faster just to add this, remove this thing here. So, then we are making it like this again. And then we are putting here an old remnant of a slab. It's lying then here, yeah? So, and here it was breaking up, you know, when they are getting old, then they are just breaking up, yeah? They are breaking up and they can hang around at this boundary in a depth of ranging between 400 and 650 kilometers. They can hang around billions of years till they are recycled, yeah? And of course, if they become recycled, then you are getting here a mixture of the material here and the asthenosphere, and this is enriched, and then you have your volcano or your ocean island basalt at the top as well, yeah? And that is now actually the more recent model, and that is also this, what you can observe here, yeah? So then we have more plus oil are the main producer of volcanism on Earth. So because intraplate volcanoes contribute between 1 and 2% of all volcanic eruptions here on our planet. So then just telling me when you are done. Then the tank can clean the board. Yes, they are still busy, sorry. Just tell him when you are done. Yes, just let me modify this sketch because then they can have the sketch number 3 for this thing, yeah? Otherwise I have to draw it again. So and now we have here a detailed model, yeah? Because what's happened now, you are producing here a bigger and a bigger and a bigger island, yeah? I mean, here in witty level, you are just producing now a very high island or with a high elevation up to 1,300 meters above the water level. So, and how does this now look like in detail? I mean, we have here, there are plums are coming up here, one coming up after the next one. So, and you have now two models, how you can describe this enrichment of the plums. It can be one model, we have the interaction with the lower mantle in a depth of 650 k's, or we have this newer model where we have old remnants of slab hanging around there. Yeah? So, but what happens now in a more detailed model? Because you are making now here not longer an active volcano, but you have here still this island, yeah? The water just goes up to here and up to there, yeah? Here is maybe Suva, here is Nandi. So again you have here your rocks, yeah? So, but here you have then a huge weight, yeah? So again then this weight is maybe here for the oceanic crust too heavy. Then it looks then like this. You are just forming here a dent. Yeah? So that is just because of the weight. So and then you are getting, then you are just deforming due to the overloading weight. You are pressing your oceanic crust also down into the asthenosphere. So there we are writing then this thing, more detailed model. Oceanic crust. Becomes deformed due to the overload. Yep. Now you know these things as well. Yep. Tell him when you are done. Yes, this one. That is the old slab, yeah. I mean, you can call it the old slab. If there are these two waters here, you have also the water flow before. Yes, that is the interaction with the lower band. That was actually the old model, and now we are seeing there are old slabs hanging around. Yep, I think we can now. Yes. So now we have a next thing where we have a plum component inside, or an enriched basalt. So what is another type locality for volcanoes where we have enriched material? It is also nearby. That is Hawaii. And therefore we have hot spot. We have a hot spot. So do you have an idea how such a hot spot chain looks like? How does it look like? I mean, you have also above the oceanic crust, I make it now something like this, because these hot spots, they are sitting on the downward chain, yeah, and I mean, as you know, I mean, the Earth is round and not a cube, yeah, otherwise it would be flat, and people would like fall down on that side and on that side. So here we have again the water. So again we have here the boundary. In 650 kilometers. So and then we have here our plum, which is rising up. And you know the mantle is stationary, yeah, I told you this also several times, and the plates are above moving, yeah. So that means the hot spot, the plum, is always sitting there, but our oceanic crust is moving to that side, yeah? So that means in our model, when the oceanic crust is moving to that side, depends always from which side you are watching it, yeah? Because then this right can be left and left can be right. Depending if you are sitting in the east or in the west of it, yeah? So now the oceanic crust is moving to that side, yeah? So where is now the oldest volcano? There. Yeah? Why on this side? If we are moving from here to here, the oceanic crust, then I mean if you are producing a volcano here and then it's moving there, then the oldest one is here. Yeah? So and that is now the oldest one, and this oldest one is not longer active, yeah? And here you have the next one, is also not longer active. And here you have the next one, is also not longer active. But this one is then active, yeah? So if you are waiting for, and that happens now in Hawaii, the volcanic chain since 28 billion years, yeah? So if you are waiting for another, I don't know, a couple of million years, then this one will also not longer be active because it is moving then there, yeah? So then you will form here the next one. So that is then the hot spot. So in such a plume can be actually very, very thick. They can last actually very, very long. Yeah, I mean, I just told you have this volcanic chain there since 28 billion years. So, and then the next thing is, before the midterm break, we did all these theoretical things. You know, the physical aspects, what happened in the magma chamber, the chemical aspects, what happens in the magma chamber, and if this is all true, what I told you, then the slopes from all these different volcanoes must be then different, yeah? So again, I will show you that this is true. You have in Hawaii, you have actually two families. Two families, but not like Singh and Kumar, I mean two rock families, yeah? Two families. So, but they are coming actually all from the same plum, yeah? And then you are creating these two families because of differentiation, fractionation, and assimilation and contamination process. But here in our hotspot case study, there it is mainly because of fractionation and differentiation within the magma chamber, yeah? Because I mean there's nothing where this well has the chance to contaminate this, yeah? At least with the material from the overriding oceanic crust. So, Therefore, we are meeting something like this, and then we making here a triangle, and we are making here a triangle, and now we have created a figure containing 3 triangles. Yeah, you know in metrology we love to make triangles. So, and using these 3 triangles, we can now show 1, 2, 3, 4, 5 components, yeah? So, and there these 5 components, these are different minerals, yeah? The different minerals inside, they are telling us what was going up here in the magma chamber. So then we have here a mineral nepheline. You know a nepheline, that is a fluid mineral which occurs only in silicate undersaturated rocks. If you are, and that you can check just in your QAPF diagram. So next to the, on this side we have also the olivine. So in the olivine, that is a mineral which occurs also only in silica undersaturated rocks, yeah? So what else do we have in such a basalt? We have the dioxide, that is a pyroxene, yeah, you know, calcium, magnesium, Si2O6. So then we are going on this side, we have the mineral quartz. So that means in this triangle here, we are forming silica saturated rocks, or describing silica saturated rocks. And on this side we having then silica undersaturated rocks. And here on this side we having very silica undersaturated rocks. And what mineral is now left on that side? That is the OPX. That is the autopyroxene. And we are using here an intermediate autopyroxene, and that is the hypersteam, yeah, that is an OPX, and that is a CPX. So, and now we have, as I told you, 2 families of rocks here in Hawaii. We have here a field. It looks like something like this, yeah? So, and these are the alkali basalts. So, and why they are called alkali basalts? Because they have a lot of alkalis inside, yeah? The alkalis, that is potassium, that is sodium, that is yeah, that is the alkalis, yeah? Potassium, sodium, and you have a lot of silica undersaturated minerals inside. So then you have here a field of different tholeiitic basalts. So when they can contain either olivine or quartz, but they are all more silica enriched, yeah? They are all silica enriched. So and then for a comparison, we have here, for example, the morgue, yeah? This is roughly the morgue, something like this, yeah? So now when we are just checking this picture, and you are checking your things what you have written down before the midterm semester break about fractionation and differentiation and all this stuff, and the gas transport, yeah, the alkali gas transport, yeah, then you should tell me, you should able to tell me to think about which type of group is the youngest ones and which type of group is the older ones. So the youngest volcanoes, that is the more recent ones, yeah? So what are the younger ones? Are these the tolleitic rocks or the tolleitic volcanic rocks, or are these the alkali basalts? Go the other way around. The youngest ones, that is the more recent one, yeah? The more recent one is this one, this is the oldest one, yeah? And the youngest one, that is these are the tolleitic rocks. Whereas the older volcanoes these are alkali basalts. These are alkali basalts. So that means the alkali basalt was removed from our plum at first, and later on the tolleitic rocks, yeah? So, and why is this? Do you have an explanation? Because I do have an explanation, but I must not have to write the examination, you know. I have written this examination in 1998. So if you are looking at such a plumb in detail, yeah? So now we are making just a bigger picture of such a plumb. So that is now a super plumb. Could also be an air balloon. So, what happens now during fractionation in our magma chamber? What is our, yes, we have the differentiation, certain minerals, more heavier minerals sinking to the ground, yeah? So the olivine is sinking to the ground and the dioxide is sinking to the ground, yeah? So they are sinking to the ground. That is a fractionation. So, but that is in the early process, yeah? I mean, you know, you are changing always the whole chamber, yeah? So, but at the beginning, I mean, the older ones, what happens very at the beginning? She is completely right. You are crystallizing the olivine, yeah? Then you are crystallizing the scleropyroxene, yeah? And what happens to this guy? I mean, the nepheline is not that heavy, but what else happened to the nepheline, because it has a very low density? That was then also separated to the top. I mean, that goes here, yeah? So then they are floating up. So in the others, they are going down. So then this stuff has been removed very early, yeah? So and I have also told you in the class, it was not only differentiation in your sense, sinking down, floating up, that is a physical process, yeah? So and what happens with the gas transport? I just told you now again that the alkalis becoming then removed to the top, yeah? That is the gas transport, yeah? So, and then you have already created such a rock, and these are the oldest ones which are sitting now here, yeah? So then this stuff has been already removed from your basalt, from the chamber inside, yeah? So, and then the younger ones becoming then more tolerific because they are becoming then more and more silica enriched. We have done this in thousands of times in both classes, yeah? That is the chemical fractionation, yeah? Did you get this? Yeah? Because the silica ones, they are the silica rocks, or the more silica enriched rocks, you are forming them also at lower temperature, yeah? So in diameter you have, and if this is all one chamber, and that is in Hawaii the case, then you are forming at first the silica undersaturated rocks as usual. They become removed at first, so they are then the oldest in the chain, yeah? So, and then you are forming, then you are removing as next the more silica enriched one, and then you are following actually this trend. You are going from here to there, from there you are going to there, and from there you are going to there. That is then the chemical trend, yeah? So you are done with this, yeah? So then we are having the different stages, yeah? The different stages. So I mean, if you are looking at volcanoes, and if you are looking on all the different volcanoes, and here I will just give you the showcase from Hawaii, yeah? Then these different volcanoes having different stages. Showcase Hawaii. So again, these different stages have different stages. When you are having a helicopter, for example, or a small Cessna, or a boat, and you are visiting all these volcanoes in Hawaii, then you know by now that they are having chemically and also optically different rocks. Do we have in our collection some Hawaiian rocks? Yes, that would be great. So then you have different, they are showing different stages, chemically wise and physically wise, yeah? But now you are at Hawaii with a boat or whatever, going around, and then of course you can see these rocks looking different, yeah, because the others are all alkali olivine basalts or nepheline basalts, and the other ones are even dolomites, which can even be appear or have some parts inside. So there we have in Hawaii the Hawaii chain. Is formed of 7 different islands. And active now is Kilauea. So what is and there we have 9 stages. So again, what is the first stage? When you are making a volcano, what is the first stage? Yeah, we are making here number 1, that we have here the oceanic crust. Then we have here the water above. Then we have here our plum. So what is this foreign stage? The volcano is still underwater, yeah? So in that we are calling then, yes, the deep marine stage. That is stage number 1. So what is after 1 if the volcano becomes then here a little bit bigger and bigger? So that is then the flat marine stage. So now number 3, what happens then? What happens at number 3? The volcano is popping out of the water. Then we are calling this the subaerial. That is the subaerial shield building stage. So that is the initial shield stage. In the initial shield stage, that is then now the youngest one, yeah, there you are forming Toleites, yeah, because the Toleites, they are the youngest one, yeah. Then afterwards, number 4. What is number 4 foreign stage? Do you have a clue? That you have done this in your experiments. The most beautiful one, which one was this? That was actually the ammoniac dichromate, at least for me. And what was this foreign stage? That was the caldera building stage. That is the caldera building stage. So then number 5, what happens after number 5? There we have the post-caldera stage. There you have the post-caldera stage, yeah? And therefore, you are forming the alkali basalts. There you are forming the alkali basalts. And one example, that is the Etna. So then we have number 6. That is the erosion stage. There's now not longer any magmatic activity. That is the erosion stage. So that means if you are running around here in Fiji, the caldera has already removed. These guys are in the erosional stage. That is now the erosion stage. So, and if you are eroding more and more and more, in the erosion stage, if you are removing always more and more and more, then I mean, what happens then to your volcano? I mean, it becomes smaller and smaller and smaller, and then it disappears at one time again underwater, underwater. So, and what happens then? I mean, it's still very close to the water, What happens there? Then you have the rift growing stage. So then you have the reef growing stage, then you are forming an atoll, Then number 8, in the Hawaiian example, I mean, is a full erosion stage that lasts between 1 and 2 MA, just in the case of Hawaii. So then in the case of Hawaii, we have then the post-erosional eruption stage. That is the post-erosional eruption stage. So and there you are forming then in the Hawaii case very silica, well you have formed there, very silica undersaturated rocks. And these are the nephelinites. So because that was actually the first stage, In the first stage where you have your remove the first melt, that was this alkali basalts from the top here, because they were formed here very first. So and then you have put them there. So but these volcanoes are now very strongly weathered, And then you have them here lying like this, So after erosion continues, then you have here the atoll stage. So yeah, if I can have just the bore. So now, in summary, we can say, yeah, that's okay. In summary, we can say the oceanic islands they consist of two groups of rocks. These are Toleites. So in these Toleites, they are olivine, hypersteam, quartz, normative. Whereas olivine and quartz cannot occur together, yeah? So when they are forming then shield volcanoes. So they are forming then shield volcanoes. So in the next group, these are alkali basalts. And they are olivine nepheline normative. So they are olivine nepheline normative. So in those rocks, or these rocks are enriched in the potassium group elements like potassium, barium, strontium, are enriched in potassium, barium, strontium, rubidium compared to bulk. Compared to bulk. Whereas the alkali basalts more enriched compared to the polyethers. So enter in the Hawaii case, polyethers and alkali basalts are formed at the same reservoir. So in that we can just prove this using isotopy techniques. Yeah. So they are formed from the same reservoir. Yeah. So this reservoir is now active in the Hawaiian chain since 28 million years. Yeah. It's a long time. Yeah. So, and I mean the plate from the oldest volcano to the youngest one has moved in the last 28 years about, I don't know how far they are away from each other. 150 kilometers, something like this. Or less, even less. So they are formed, no, it must be more. Yeah. I will just check it how much it is. So these polyethers, they have here a higher melt degree because they are depleted compared to the alkali basalts. And these alkali basalts have then a lower melt degree. Because they are compared to the polyethers enriched. In those elements. So again, in summary again, we have the plum, and we are forming the first polyethers. And the plate above, the oceanic lithosphere above, is moving So now the thing is, I think to finishing the class, because we lost 3 times, yeah. One time was because of Easter Monday, and one time we lost because of the cyclone, and the third time we lost because of the filtering. So I need actually 1 double hour more. Yes, when can we do this? Huh? Thursday, Wednesday. Yes, then let us meet here on Wednesday between 3 to 5, yeah? Because the dean has already sent, or HR, or I don't know who, has already sent an email around that I should make an agreement with you to every lecturer, yeah? How we can get this time in which we lose, yeah? So I need actually 1 double hour more than we are done. So then we are making Wednesday 3 to 5 here, yeah? Okay, and I mean the others can go downstairs and making the singing, yeah? Okay, then see you Wednesday 3 to 5, between 3 and 5, yeah?